Lecture 6.5, Macroscopic Ohm's Law and Resistance. We've just studied the microscopic form of Ohm's law. Now we're going to focus on the macroscopic one. So if I look at the microscopic, we wrote that the applied electric field divided by the current density, that this was a direct proportionality. And we found out that this was the resistivity, which we defined as rho. This guy here is material dependent. But now we're going to the macroscopic form. And this is what it says. If there's an applied voltage over the current, this is also a constant. But this constant is defined as resistance. And resistance is very similar to capacitance, as we'll find out in a moment. So this is also material dependent. So this is our form of Ohm's law right here. So we've studied, believe it or not, resistance already, but just in a different form. I would say that we've studied capacitance and resistance plays a similar role. So what did we learn about capacitors? So if I talk about capacitors, here's what we said. So for capacitors, we did the following thing. We had our first circuit element, and this element, of course, is the capacitor. And then symbolically, we drew it as two parallel plates, of course, with the dielectric inside. So this here is our capacitor with capacitance. Then we had our law. Our law, which we call the capacitor equation, but it's the law of capacitance. So this is the capacitance equation. And to just continue in the line of Ohm's law, I'm going to call this also a law. And what we found here is that the capacitance was defined as the ratio of charge divided by voltage. But that was only half the story. It didn't tell us about the characteristics of the capacitor. So then we came to what I call the characteristics. So the capacitors characteristics tells us about the details of the capacitance. Or maybe I should have said the capacitance characteristics does that. But here's what it says here. So if I have a capacitance, That depends on the dielectric material inside the capacitor, and it also tells us about the capacitor's geometry. So when we put that all together here, we had the permittivity constant times the geometry, which is about the area and the plate separation. So then what we did here is that we started to draw our capacitor. So when I'm looking at this capacitor here, what we're seeing is that it's two plates. And when I'm looking at these plates, we're going to say that this is the upper plate. And of course, that's the bottom plate. But the one thing that we should think about is that this has a dielectric inside right here, right? That's our dielectric right there. So then to top it off, we then have our wires. So what does this tell us? That tells us about the area. This tells us right here about the plate separation. D, and then of course inside here is the permittivity, epsilon. It tells us about the dielectric. And so we replace this with this symbol for the capacitor. So that tells us all about those details. Now we do the exact same thing. I played the same game that I just did, but now we're talking about resistors. So resistors are described in a similar manner. So it has all of the same types of things. So then the first thing that we want to talk about is that what's the circuit element? So the circuit element is a resistor. And we typically write that as R, but symbolically, it looks like this. Then we have our equation, our law, and we would say that this is the resistor equation. But in this case, they call it a law. What do we mean by the law? We mean Ohm's law. And so when I look at this, we then say that the resistance plays the exact same role as the capacitor equation, where the ratio of voltage to current gives me that material dependent constant. When I say material dependent, I mean the whole package. And then what we find here is that the resistors characteristics is described by the resistance. Which tells us about the resistor details. So what I'm saying here is that resistance is the whole package that includes both material. And when we studied the material, this was the resistivity. If we had not talked about resistivity separately, I wouldn't have done this. And the geometry dependence. So if I put this all together, we could then say that we have this quantity called the resistance, which is the characteristic equation of resistors, which then tells us about the resistive material times the resistors geometry, and this is equal to the resistivity. And as we will find out, resistivity is a function of temperature. So I'll put the temperature in here times the length of the resistor divided by the area. So this is the resistivity. So if I look at this picture-wise, what am I seeing here? Well, I have a resistor. And that's the symbol. Now what I'm going to have is that I'm going to have a cylinder, and we're going to draw an effective picture, which is what I'm drawing now. And then it's going to look something like this here. So what you're finding here is that you're finding something like this. This right here is a wire, just like with the capacitor. I'm going to define the area right here. So this guy right here tells us about the area of the resistor. This guy right here, this is the, right in here, we're going to say that this is the resistivity, which we defined as rho. And then what we find next is that we have to worry about the length here. And so when I look at this guy, it turns out that this quantity here represents the length L. So that's what it looks like right there. So what we want to do is that we want to model a resistor. And the way we're going to do this here is that we're going to model a resistor as a restriction in a wire where the wires are thicker than the resistive part. So to get a sense of this, let's imagine something like this. Imagine that we have a wire. So here's my wire, and there's no restriction here. And now what I'm going to do is that I'm going to insert a resistor. So when I'm looking at this, I imagine that I have a current that's coming in like this. Right? So in this sense, this is my current. And as I said before, this is my wire. now what I'm going to do is that I'm going to do the exact same thing, but now if this is 2 squares, I'm going to actually put in a restrictor. In other words, I'm suddenly going to make a smaller area or diameter right there. So in other words, this is the wire in gray, but when I look at this yellow part here is the resistor. So when I say we're going to model, this is the resistor. And what you're going to see here is that this restriction causes a decrease in current. So again, I still have current coming in here, right? I still have current coming in here. But we're going to find here, and in a little bit, that the current isn't going to be reduced. But that's what we mean by a resistor. So once again, the gray is the wire. The yellow part is the resistor. So let's start talking about this. Now, I'm going to have to do some technical details to tell you how current actually flows. And so maybe I should write something down so that it's a little bit more clear. So there are some technical details that need to be addressed. Mainly, it's how current flows through a resistor where a wire is thicker and the resistor is thinner. How does it do that? How can it do this? And once again, it's all about setting up a potential difference. So that's what we're going to have to do. I have to show you why there's a voltage in the circuit when there's a resistor in it. So here we go. We're going to start with an analogy. And let's say here, the analogy is something that you're very familiar with. And we're going to look at water restriction in a water hose. So here we go. When water is flowing out of a hose, its rate is constant according to what is called the volume flow. So when water comes out of a garden hose, its rate is constant according to the volume flow equation. And it's really just saying that this is what we mean by water current. So in this case, we have a hose and we define this thing called the volume flow. So if you've done some type of fluid dynamics, you would know this. And this is equal to the area of the hose times the speed. And here's the important thing. That quantity in a circuit, in a water circuit, whatever you want to call it, is always constant because it always has the same pressure. In other words, if this is constant, then if I have a large area, then the speed of the water flow is slow. If I have a small area, then the speed of the water has to speed up. And that's what we need to analyze right in here. So if you partially block the opening of the hose with your thumb, you've decreased the area. Which causes the water to shoot out faster and farther. And I'm sure you've done this at some point. And so this is what I mean here. So let's imagine that we have a water hose. And let's say, here's my water hose right here. And then at the end, we have our end right here. So when I'm looking at this guy, we're talking about water flow coming through this thing. Now, what I want to do here is that I want to copy this because I want to make two images of this thing. Okay, so here we go. So if I'm looking at this, this is what I would see here. If this is unrestricted, okay, so if I'm going to say that there is no restriction, you're just letting this thing just shoot out. What am I going to see here? You're going to see that the water shoots out a distance something like this. Right, so the water comes out and it's going to go some distance. And what you're going to find here is that this distance is going to be small because now the speed that's coming out is going to be small. On the other hand, if you now put your thumb over, so there is restriction now, you got partial blockage. And as a consequence, what's going to happen? The water shoots out farther. And the only reason it shoots out farther is because it has to conserve volume flow. Smaller area means it's got to have a higher speed. So therefore, this speed is then going to be higher. And we see that because it travels a farther distance. So in this case, here's what we're seeing. According to the volume flow rate, we have in this case, we have a large area and therefore a smaller speed. So this is telling us no restriction. If we have no restriction, that means it's a larger area. So therefore, the water comes out slower. On the other hand, if we put our thumb over it, we have a smaller area, but a higher speed. In other words, this guy now is faster. And in this situation, we find that we have a restriction, which tells us it has a smaller area. Now, here's the whole reason why I wanted to do this. The only way to change the speed of the water is a pressure increase. You need a pressure increase. That is, by you putting your thumb over the water, there's a higher pressure. So a pressure difference increases because of the restriction. And we won't go into the details. And so what we're finding here is that, so when I look at this pressure difference, that means it's going from a high pressure region minus a low pressure region. And it's this pressure region that causes an increase in kinetic energy. That's what we're here for that reason right there. We need that pressure region. So now, if I was to draw a picture of it, then it's going to look something like this. I imagine that I have my hose. And as I have my hose, I now restrict the flow of the water. And so here's my green hose. Here, I have my water, right? So in this case, this is the hose, and here, this is the water that's coming out. And so what you're seeing here is that I now have a high pressure here, and now this is a low pressure, and as a consequence, I now have slower water versus faster water. So if I'm now going to make this jump to electric circuits, the pressure difference is the same as the potential difference, which means there's a voltage. Applying this analogy to electric circuits and resistors, the potential difference, in this case, it's potential, but we were just talking about in the language of pressure. The potential difference in other words, the voltage between the wire and resistor causes an increase in drift speed. So I can come in here and I could take this exact same thing, right? It's the analogy transfers extremely well. So the only thing I'll do here is that we don't have a hose and we don't have water. So what do we have? What we have is that we have a wire, right? This is my wire right here. And when I look at that wire, what ends up happening is that this now represents a high potential. And because I have a high potential, what am I going to get? I'm going to get a slower drift speed. In other words, my drift speed here is going to be lower. Now, when I look at the resistor portion of it, this right here is now our resistor. And because it's the resistor here, this now represents a low potential. And because it represents a low potential, we're going to see that the drift speed now has increased. So in other words, we have a faster drift speed. So now our job here is this. How is this potential difference / voltage created? And as a consequence, it's going to tell us how Ohm's law sets up voltage, current, and its connection to resistivity. So the way I'm going to answer this question is that I'm going to go through another analogy. So the analogy I want you to think about is that we want to talk about a bottleneck in traffic. We're all familiar with bottlenecks. So as an example here, if a 2-lane road is suddenly restricted to one lane. And in my mind, I could imagine that there's a car accident. There's a sudden car accident, and you're suddenly going from 2 lanes into 1 lane. What happens? There is a temporary blockage before things get settled here. But the temporary blockage of cars reduces car flow. After, things have settled, then we get motion again. So picture-wise, again, we imagine that we're going into 1 lane, right? So here's our road. And I'm thinking this is lane 1, lane 2, and it's now a restriction. So this analogy is important because of what has to happen. So right in here, we're seeing here that cars get backed up temporarily. And the reason why that is there's this restriction here. So when I look at this, there's this restriction caused by a smaller area. So what happens with the electrical resistors? Effectively the same thing. With electrical resistors, there is a sudden restriction from the wire to the resistor, right? In other words, there's a temporary blockage. And because of that sudden blockage, and this causes a charge buildup between just a charge buildup. The volume flow tells us about how much the drift speeds are going to change. So the volume flow tells us how much the drift speeds change according to the voltage. So once again, when we talked about these wires, earlier we knew that we had to go to potential from a high potential to a low potential. So now what we need to do is that what does that mean? So what I need to do here is that I need to try to draw a picture. So here's what we want to do. So if there is a charge separation, then we then say that if I have a smaller charge separation, that means I'm going to have a smaller voltage, which then gives me a slower drift speed. If I have a larger charge separation, then I'm going to have a larger voltage, which then tells me I'm going to have a faster drift speed. So now let's look at this thing. In order for current to flow in a wire, there has to be a voltage. Okay, so let's see if we can summarize these things. So let's summarize all of this in pictures. So the first thing that we have to look at for current to flow in wires, there must be a potential difference or a voltage. So in this case, what we want to do is that we want to look at the voltage between the wire and resistor. So if I do that, I imagine that I have this now. I have this guy here. And I'm only going to look at half of this thing. So if I look at half of this thing, here's the wire. And then here's the resistor. So if I look at this thing, we can see here is that this is going to be the wire. And over here, I'm going to have the resistor. So what you're seeing here is that I have a charge. And because I have a charge, you know what? I'm going to draw this out separately because I'm going to need this numerous times. So I'm going to come in here and I'm going to put this guy and I'm going to copy this guy. So I'm going to copy this so that I have access to it again and again. So now here's what I have. I have a charge. And this charge is moving in the wire because it's a fat wire. I have a small drift velocity. So when I'm looking at this, I need a voltage across that. Otherwise, that charge will not move. So I'm going to make arbitrary charges. So I'm going to say that this guy has to have a smaller charge. This guy has to have more charge. And when I have more charge, what we're going to see here is that we've now developed a voltage along the wire. So that wire tells us that it has a small voltage across that. So then I'm going to say that I have a smaller charge difference And if I have a smaller charge difference, then I'm going to have a smaller voltage. And if I have a smaller voltage, then that means I have to have a lower drift speed. But same current. And in this here, I have a bigger area, a smaller drift speed, and that has to stay a constant. Now, let's look at the voltage across the resistor. So the drift speed must increase through the resistor. And the reason why is because we know that the volume flow rate has to remain a constant. So if I now have a restriction, that means that my area is smaller. So therefore, the drift velocity must be large. But if I have a large drift velocity, I must have a higher voltage. So now let's draw that picture. So what I'm seeing is that I have my resistor that's going to look like this. So I have my wires. And what I'm seeing here is that now I have my little charge. Let me grab this charge. And I'm going to place this charge in here now. So when I look at that charge in here, what am I seeing here? Well, for starters here, that means that I have to have a higher drift velocity. We saw here that this drift velocity was small, but now I have the restriction. So that means this drift velocity has to be large. And the only way that could happen is that if I have a larger push. So I need a bigger charge separation. So if it starts here at 4 charges, what I'm going to do is that I'm going to put my reference of 0, and I'm going to say that that's 0 volts. So now I'm going to say that this guy is now negative. Now remember, these charges are arbitrary. But what this is telling me here is that I went from what? I went from 8 to 4. That's a 4 charge difference. Here, I'm going from 4 to 0, and then from 0 to 4. That's an 8 charge difference. So that's a bigger charge difference between the two. That's why I have a bigger voltage. So now I start the process. When I look at this, I have a larger, you know what? I should just get this right here. This is the same thing. So if I copy this, I could now just place this guy right here. And then I'll just modify it. So what does that mean? So it's not smaller. I now have a larger charge difference. As a consequence, I'm going to get a larger voltage. But we knew that because we started saying that this had to be a faster or higher drift speed, but the current has to be the same. So now the big difference here is that now I have a little area, but I have a huge drift velocity. So now I know what that is. So now, if we put this all together, I mean, we should deal with the other end, but it's got to be the same type of thing here. Maybe we should do that. And the third step here, now, if this is my wire here, and I know that I have a small drift speed, then this must also have a small drift speed in this part of the wire. So what I'm looking at is that I'm now looking at this half of the wire system. So if I look at this, then what I'm trying to do here is that I expect a smaller voltage from the resistor and wire on the right. And so since we've already done this, we could, really just talk about this very quickly. And so what I'm seeing here is that when I look at this thing here, I do start off with a higher drift velocity. But now, in order to have a smaller drift velocity, what do I have to do? I have to have a smaller voltage change. So -4, and this is -8. This here creates a high, and this is a low. So you could see here is that now we have a smaller voltage across because we're now in the wire. So now we can put this all together. And this is where Ohm's law becomes very powerful. So now, putting this all together, and it looks like this. I have a wire that has a restriction. So when I do this, there is a certain amount of charge distribution in order to keep current, moving here. So I'm going to say that in this wire, if I summarize all of the charges, then this is what I'm seeing. I'm seeing that this is 8 charges here. This is 4 charges here. So this here has to be the voltage of the wire. So when I look at this thing, that's the charge difference. So when I look at my charge here, what am I seeing? I have 3 charges that I have to pay attention to. And here's what we're looking at. So I want to place this in 3 spots. So I want to go here, here, and then finally here. So what should I expect? And the wider portions, we should expect that this has a smaller drift velocity. This one has a higher drift velocity, and then this one is smaller. So now that's telling me about the charges. So in this case here, you're seeing here is that in this section, I have 4, and this one, I have 8. So once again, this is telling me about the voltage of the wire, but right here, this gives me a big voltage across the resistor here. just by looking at the drift velocity. Now, what do the voltages look like in the circuit? So if I plot these voltages, let's say that I'm only looking at these regions right here, because my drift velocity is smaller, my voltage has to be less steep. So I'm going to come in here and I'm going to say, this has to be less steep. And if I come over here, this has to be less steep. So when I'm looking at these voltages of the wire here, they're going to be the same. So this is telling me right here that that is the voltage of the wire. That's what's making the charge move through the wires. This right here is also the voltage of the wire. But now I have a huge drift velocity. And because I have a huge drift velocity, this has to be steeper. And so when I'm looking at this guy, you can see here is that now this is the big voltage drop across the resistor. So when I go and I look at the drift velocities, let me see if I still have that little charge. I do. So now look at that. I can place one here, here, and then finally here. So what do I see? Why is the drift velocity the way it is? Because this is going down a very low incline. And then when it gets to the resistor, it now has a high drift velocity because the incline is steep. And then here, this is a low incline, so therefore a smaller slope.